Okay, when you did your scatter plot, you should have ended up with a graph that looks something like this. And you can see that it's clearly, it's pretty nonlinear. Looks like it definitely has a curve to it. As a reminder how to do that on your calculator, you need to enter your data into L1 and L2. And then if you press zoom, if your stat plot is set up to go, it needs to be on. You need to have a scatter plot selected, and L1 and L2 need to be in there. You can just select it to make sure that it looks that way as well. And then you're going to press zoom and then number 9 for stat. And then you can see the scatter plot, and we can see that the distribution looks nonlinear. And then to get the regression equation, you can press stat and then calc. And then we want number 4, which is linreg. And then you just go through to calculate, and we can see here. So if you pick number 4, it says that the equation is y equals ax plus b. That means on the calculator, a is the slope and b is your y-intercept. A is the slope because it's the one with the x. So then when you write your equation, your slope is going to be 1.605, and your y-intercept will be negative 3,222.63. So that's what I have here. You can also put it in terms of the variables that we have. The units sold are what we're trying to predict, and the year is the variable we're using to predict. So then in order to find the residual for 2007, first you have to find the predicted value for 2007. So you plug 2007 in for x, and you get negative 1.398. And then the residual is the actual y minus the predicted y. So remembering AP, actual minus predicted, it turns out to be 1.898. So the actual number of units sold were greater than predicted by 1.898 million units is the way we would interpret that. All right, so then next you were asked to find the residuals for each year and then plot them against the year. And when you do it, this is what you end up with. This graph of the year, the explanatory variable, on the x-axis, and the residuals on the y-axis is called a residual plot. So if we look here, the points where the actual was greater than the predicted, those are where we have our positive residual. Okay. Same thing over here. And then where is it less than predicted? Those are here. The negative residuals. And you can see that then if you look at this residual pattern, it goes positive, then it goes negative, and then it goes positive again. So that makes this, this is indicating that our original data was actually curved. And you can see if you were to look back at the scatter plot up here, right, the first ones were above the lines, the next group is below the line, the least squares regression line, and then we're above the line again. And that's exactly what the residual plot is showing us. Okay. So you can, sometimes it's actually hard to see in the initial scatter plot whether or not there's a curve. There are some cases where it actually looks pretty straight, but if you look at the residual plot, you can see a pattern in the residual plot indicating a curvature to your data. So the residual plot is another way to check whether or not your distribution is linear or nonlinear. All right, so the things that you looked at already were the least squares regression line. That's the line that makes the sum of the squares residuals as small as possible. The residual plot is a scatter plot that displays the residuals on the vertical axis and the explanatory variable on the horizontal axis. When you're interpreting a residual plot, ideally you're looking to see that there's no curved pattern in the residual plot. And if that's true, then the linear regression model is going to be appropriate. So ideally we want to see an unstructured horizontal band of residuals centered around 0. This is sometimes hard to achieve with small data sets. So we just want to make sure there's not a curved pattern, like going from positive, negative to positive, or the other way, negative, positive to negative, like you saw in the problem that you guys worked on. And if there is a curved pattern in the residual, we would need to use a different model with a different form, and we'll do this later in the course. Okay. So looking here at this first graph, scatter plot. So here's the scatter plot here, and then down here is the residual plot. You can see that the distance is on the x-axis on both the scatter plot and the residual plot. It's the y-axis that changed. And if you look here, we can see that this is kind of an unstructured horizontal band centered around 0 in terms of these residuals. So that would mean that, yes, the residual plot shows an unstructured horizontal band centered around 0 so a linear model is a good fit. In the graph on the right, we can see in the residual plot that there is a definite curve here. So the answer to this one, whether or not a linear model is a good fit, would be no. The residual plot shows a curved pattern so the linear model is not a good fit. All right, so the next thing I want to go over is reading computer output. All right, so when you are reading computer output and you're looking for the least squares regression line, what you need to look for is the word coefficient. So we have coefficient here, and here we have percent, and here we have constant. So the constant is going to be your y-intercept, and this percent is going to be your slope because it's your x variable. Okay. And so in this problem, we're trying to predict age from the percentage of a tooth roots with transparent dentine. So when we're writing the least squares regression line, y hat is the variable we're trying to predict. Our slope is here. It's going to be the 0.5549. And then we'll put an x. And then we'll put plus our coefficient for our constant term, which is our y-intercept, which would be 32.08. And then we should define our variables. So y hat is our predicted age, and x is the percent of a tooth's root with transparent dentine. All right, so our slope, we said, is the change in y over the change in x. And actually, it's the change in y hat. So it's going to be 0.5549. And we're going to assume that the units on our predicted y is years. And then it's going to be over 1% of a tooth root with transparent dentine. So when we go to interpret this, we start on the bottom and we say, for each additional percentage of tooth root with transparent dentine, predicted age increases by 0.5549 years. And it's important to have that word predicted in there. So now when we are looking at y-intercept, that was 32.08. And that's when x is equal to 0. All y-intercepts are when x is equal to 0. So in this context, we would say that a person with no transparent dentine on the tooth's root is predicted to be 32.08 years old. All right, and then the last part asks us to find and interpret the correlation coefficient for the data. So we need to go back up to the output. All right. And correlation coefficient is R. On the output, there are two places that we can look that involve R. There's R squared and there's R squared adjusted. R squared adjusted is beyond AP statistics. That's for a secondary course. Ignore it. We don't use it. So the one that we want is this one right here, the R squared. So if R squared is 28.6%, we're going to come back down here and we're going to say, well, R squared is 0.286 because R for us is a number between 0 and 1. So then that means that R is either plus or minus 0.535 if you take the square root of 0.286. So to decide whether or not it's the positive or the negative value, you look at the slope. In this problem, the slope is positive. So that means that R needs to be positive as well. So then R is 0.535. So then interpreting correlation coefficient, you need to talk about the strength. So 0.535 would be a moderate. We want to talk about the direction, positive. We want to talk about the shape. We don't have a scatter plot to look at, but R only tells us about a linear relationship. And then we want to finish off by using context. So between age and the percent of a tooth's root with transparent dentine. Okay. So on the next page we have one more. So let's look here. Again, we're starting by looking for the slope and the y-intercept, so we need to find the equations. We want to look for the word coefficient to figure that out, so this time on this output it moved up a little bit. It's not in the same spot. And this time, constant, that's still going to be our y-intercept. And in this one, our slope is going to be the coefficient of what they're calling x. So this data is about quit rate versus average hourly wage for an industry. So in this problem, our slope is, again, change in y hat over change in x. So it's negative 0.34655, and that's our quit rate, which is quits per month. As a percent of employment. And then it's over 1, and what is our x unit? Our x unit is the average hourly rate. And we're going to assume that's in dollars. All right, so interpreting slope, we would say as average hourly wage for an industry increases by $1 per hour. The predicted quit rate decreases by, and it's decreasing because we have a negative slope, 0.34655. Okay. Now, interpreting the y-intercept in this context, well, the y-intercept is up here, whoops, and it is 4.8615. So remember, y-intercept is the value you get when x is 0. So for an industry of volunteers, or an average hourly wage of $0 per hour, has a predicted quit rate of 4.8615. All right, then last we want to find the correlation coefficient of the data. So we're looking for r squared to start because the output doesn't actually have r. We ignore the r squared adjusted. We're not ever going to use that in this class. And we want r squared. So r squared in this case is 0.729. So if you take the square root of r, that would be plus or minus 0.854. But then we have to decide which one. The slope is negative. So that means that the r we want is negative 0.854. And I didn't ask you to interpret this time, but if you did, you would say that there is a strong or very strong positive linear relationship between average hourly wage and quit rate.